And now we explore the last population parameter we might be interested in for two different populations, the variance. Generally speaking, we said that variability is often viewed as a bad thing. Variable processes and systems make predicting system behavior, or depending on particular behavior, difficult. And so we, as engineers, may often want to know how the variability of two processes or systems compare with each other. Is the variability in the diameter of output from this machine the same as it is for that machine? Is the variability in the weight of component parts from supplier 1 the same as from supplier 2? Is the variability in measurements from one bridge inspector the same as another bridge inspector? And so on. We start off with a confidence interval for the ratio of variances of population 1 and population 2. This confidence interval is a little tricky. Because of the nature of the F distribution, it doesn't follow the pattern of point estimate plus and minus a margin of error. We know that S1 squared over sigma 1 squared divided by S2 squared over sigma 2 squared follows an F distribution with N1 minus 1 degrees of freedom in the numerator and N2 minus 1 degrees of freedom in the denominator. To find a 1 minus alpha times 100% confidence interval for this ratio, we bound it by an F value with alpha over 2 in the upper tail and an F value with alpha over 2 in the lower tail. Of course, the alpha over 2 in the lower tail corresponds to 1 minus alpha over 2 in the upper tail. But we're ultimately interested in a confidence interval for the ratio of sigma 1 squared to sigma 2 squared. The ratio of these two variances gives us an idea about how different they are. If the ratio is large, then the variance of population 1 is likely greater than that of population 2. If the ratio is small, then population 1 is less variable than population 2. With some algebraic manipulation, we isolate the ratio of sigma 1 squared to sigma 2 squared and find bounds for this ratio as a function of sample variances and F values. Note that the degrees of freedom are reversed from the bounds of the previous ratio. That's due to the algebra required to isolate the ratio of sigma 1 squared to sigma 2 squared. Working out this algebra would make a great homework problem. So let's put this confidence interval to work with an example. Say that two different chemical companies can supply a raw material. The concentration of nitrogen in this material is important. The mean concentration for both suppliers is the same, but we have reason to believe that the variability in nitrogen concentration may be different between the two companies. The standard deviation of nitrogen concentration in a random sample of 10 batches produced by Company 1 is 4.9 grams per liter. For Company 2, a random sample of 16 batches yields 5.8 grams per liter. Let's find a 95% confidence interval for the ratio of variances of nitrogen concentration for the two companies. Let's first look up the F values. The degrees of freedom for population 1 are 10 minus 1, or 9. For population 2, we have 16 minus 1, or 15, degrees of freedom. For the upper bound, we need a value of F with 15 degrees of freedom in the numerator, 9 degrees of freedom in the denominator, and an alpha over 2 of 0.025 in the upper tail. We go to the table for 0.025 in the upper tail, we go over to the column associated with 15 degrees of freedom in the numerator, and down to row 9. That intersection is 3.77. To find the F value in the lower bound, we have 15 degrees of freedom in the numerator, 9 in the denominator, and we want 1 minus alpha over 2 in the upper tail. That's equal to the inverse of the F value with degrees of freedom reversed and just alpha over 2 in the upper tail. We go to the F table for 0.025 in the upper tail, over to the column for 9 degrees of freedom, and down to the row for 15 degrees of freedom. And we find that the F value is 3.12. 1 divided by 3.12 is 0.321. So the upper bound on the confidence interval is 4.9 squared divided by 5.8 squared times 3.77, which is 2.69. The lower bound is 4.9 squared divided by 5.8 squared times 0.321, which is 0.23. So the ratio of the variance of nitrogen concentration in the material produced by Company 1 to that produced by Company 2 lies between 0.23 and 2.69 with 95% confidence. We could also say that we're 95% confident that the true ratio of standard deviations lies between 0.48 and 1.64 by taking the standard deviation of both sides. This suggests that Company 1 is as little as half as variable, up to roughly 1.5 times as variable as Company 2. Based on this result, we can't really draw strong conclusions about which company produces a more highly variable product. And of course, we must also talk about hypothesis testing. We might want to know if the variance from one process or system is equal to that of another. We could have an equality statement in the null hypothesis with less than in the alternative. Or we could have greater than in the alternative. The same three options as always. The test statistic is F0, the ratio of S1 squared to S2 squared. If the ratio is large enough, maybe the variance in population 1 is larger than that of population 2. Likewise, if the ratio is small enough, maybe the variance of population 2 is bigger. And of course, large enough and small enough is determined by the rejection region of size alpha. The critical value and p-value approaches still apply. The critical value approach is a little easier with tables, and either approach is made easy with Excel. Some textbooks suggest to always put the larger of the two sample variances on top to force an upper tail test. But accounting for two-tailed, upper tail, and lower tail tests lead to a better understanding of what the test statistic is really telling us. Let's take a look at an example. There's a field of mathematics that studies waiting in lines, from people standing in line for an attraction at an amusement park to raw materials waiting to be machined on a factory floor. The fancy word for a line is a queue, and the field of mathematics that studies queues is called queuing theory. One thing we learn from queuing theory is how to design lines. Most service counters, say at a bank or at a fast food restaurant, have one of two kinds of queue designs. The first is where there is a number C of servers behind a counter, and C corresponding lines form for customers to wait for an individual server. When a customer enters, he or she would rationally try to get in the shortest of the C lines. But of course, there's no guarantee that this leads to the shortest waiting time, as the service time for customers ahead of them could get lengthy. In the second queue design, a single queue is formed, usually with a barrier rope. When the server finishes with a customer, the next customer in the front of the single queue approaches the counter. As it turns out, the average waiting time for these two designs is roughly the same. However, the variability of waiting time can be much larger for the first design. Waiting in line behind an occasional, especially lengthy customer can lead to periodic waiting time values that are longer than others. Thus, this leads to variability in waiting time. Let's say we set up an experiment to explore the difference in variances in waiting times resulting from these two queue designs. And we want to know, is the variability of the individual line, which we'll call population 1, greater than that of the variability of a single line, which we'll call population 2. Say we collected a sample of 25 individuals serviced in individual lines under conditions of average busyness, and we found a standard deviation of waiting time of 2.3 minutes. And we collected a sample of 16 individuals serviced from a single queue, and we found that they had a waiting time standard deviation of 1.1 minutes. The test statistic is 2.3 squared divided by 1.1 squared, which is 4.37. We have 25 minus 1, or 24, degrees of freedom in the numerator, and 16 minus 1, or 15, degrees of freedom in the denominator. Let's say we want to implement the p-value approach using the f-tables. The smallest area in the tail which we're given in the table is 0.01. And going over to the column associated with 24 degrees of freedom in the numerator and down to the row for 15 in the denominator, we find 3.29. Our F0 statistic of 4.37 lies beyond 3.29, suggesting that the p-value is smaller than 0.01. A small p-value, smaller than most any alpha we'd ever choose, leads us to reject the null hypothesis. Based on our samples, we would conclude that the variability of waiting time resulting from multiple lines is indeed larger than that resulting from a single line. We can use Excel to get a better estimate of the p-value. With the fdis function, we find that the p-value is 0.0024. Again, a very small number. And so, that sums up statistical inference for differences in population variances. Recall that in statistical inference for differences in means, we have two different approaches depending on whether we can assume that the variances of the two populations are equal or unequal. As you might imagine, we can first perform a statistical comparison of variances with an f-test to determine whether they are equal or unequal before we then proceed to the appropriate t-test for comparing means. It's common practice to perform statistical tests for various assumptions before performing the ultimate statistical analyses that you might want to address.